Every day, Earth is quietly pelted by over 100 tons of tiny, sand grain-sized space particles, and we barely notice. Once a year or so, a car-sized rock screams through our atmosphere, putting on a spectacular light show before disintegrating harmlessly overhead. Step up the scale to kilometers across, and we're talking extinction-level territory, but thankfully, those arrive only once every few million years. We haven't had one since the dinosaurs. Fortunate timing for us. But here's an uncomfortable thought. Size alone may not be the most dangerous variable. According to one fascinating scientific theory, certain extraordinarily rare space rocks could be made of something far stranger than stone or iron, and their destructive potential would utterly dwarf even the largest nuclear weapons ever built. From the outside, you'd never be able to tell these apart from ordinary meteors. In the vacuum of space, they'd look completely unremarkable. But the moment one of these objects encountered Earth's atmosphere, the resulting explosion would make nuclear warheads look modest by comparison, and those would be the small ones. A kilometer-wide version? We might not have a planet left to discuss. That is the terrifying potential of an antimatter meteor. Could such objects actually exist? What scientific signals might help us distinguish them from ordinary space rocks? And how large would one need to be before it became a genuine planetary catastrophe? I'm Alex McColgan, and you're watching Astrum. Today we're putting the science of antimatter meteors under the microscope and examining just how plausible their existence really is. Antimatter is a peculiar substance, and the simple fact that it exists is something of a paradox, because by all rights, we shouldn't be here to study it. It is nearly identical to regular matter in almost every way, with two critical distinctions. First, its electrical charge is inverted. Second, and far more dramatically, when antimatter comes into contact with ordinary matter, the two obliterate each other entirely, converting almost completely into pure energy. Cast your mind back to the Big Bang. In those first extraordinary moments, theory tells us that matter and antimatter were produced in roughly equal quantities. Every particle of matter should have found its antimatter twin and annihilated, leaving behind an empty, structureless universe. No galaxies, no stars, no planets, no us. And yet, here we are. For reasons that physicists are still actively working to understand, slightly more matter than antimatter emerged from those early moments, perhaps as small a difference as 1 billion and 1 matter particles for every billion antimatter particles. That fractional imbalance is the entire reason the observable universe exists. Scientists haven't yet cracked why this asymmetry occurred, but the mystery remains one of the most tantalizing in all of physics. The consequence of this is that our universe is overwhelmingly composed of regular matter. The only places we reliably produce antimatter today are high-energy particle accelerators like CERN, and some hospitals even operate small accelerators to generate positrons for PET positron emission tomography scans. But just because antimatter is rare doesn't mean it's entirely absent from the cosmos. When the dense, hot quark gluon plasma of the early universe began cooling and organizing into particles, the overall balance favored matter, but not uniformly. Local fluctuations would have occurred. In certain pockets of the early universe, antimatter could have temporarily dominated, and if those pockets were large enough and sufficiently isolated, gravity could have drawn them together. Rather than being annihilated away, these clumps of antimatter could have grown, forming protoplanetary disks, solar systems, and stars made entirely of antimatter. In such a region, it would have been ordinary matter that appeared as the minority, eventually wiped out, leaving behind a fully antimatter stellar system. This remains highly theoretical. But could such systems genuinely exist? Remarkably, there's at least a hint of evidence. In 2021, the Fermi Large Area Telescope identified 14 candidate stars in the Milky Way that emit gamma radiation in patterns consistent with what we'd expect from antimatter stars produced when regular interstellar matter encounters. Their antimatter surfaces and annihilates. These objects aren't definitively confirmed as anti-stars. Pulsars and black holes can produce similar signatures, but the profiles are not inconsistent with the antimatter interpretation, suggesting a ratio of roughly 1 anti-star for every 400,000 regular stars. If anti-star systems exist, it's not a large logical leap to suggest they'd also host antimatter asteroids, comets, and meteors. The concept of antimatter meteors reaching Earth is actually older than you might expect. As far back as 1940, barely a decade after antimatter was first theorized, Russian-American physicist Vladimir Rojansky was already speculating about their existence. The mechanism is straightforward enough. If our solar system passed within gravitational range of an antimatter stellar system at some point in its history, the sun's gravity could have perturbed outlying antimatter objects from their orbits and captured them. Antimatter couldn't have formed natively within our solar system. Any antimatter particles would have been rapidly annihilated in the particle-dense environment of the early solar nebula. But in the near vacuum of deep interstellar space, with almost nothing to react against, an antimatter rock could theoretically survive for an extended period. So could one be drifting silently through our neighborhood right now? American astronomer Lincoln LaPaz was among the first to seriously consider whether any of Earth's ancient impact craters might carry the fingerprints of an antimatter strike. To properly evaluate that question, we need to think through what such an impact would actually look like. The journey wouldn't be straightforward. Any antimatter meteor approaching Earth would first have to contend with our atmosphere, and that creates an entirely different challenge compared to a regular meteor. When an ordinary rock from space plunges into the atmosphere at high velocity, friction generates enormous heat, burning away much of the object before it reaches the ground. The result is the familiar luminous streak we call a shooting star. An antimatter meteor would suffer a far more dramatic fate. Every single atmospheric particle it encountered would annihilate an equivalent amount of the meteor itself. This brings us to Einstein's famous relationship, E equals mc squared. The meteor's mass, multiplied by the square of the speed of light, tells us the energy released, and because each annihilation event destroys both a fragment of the meteor and a fragment of the atmosphere, the effective energy release is roughly doubled. Let's run through some approximate numbers. While the technical boundary of space sits at either 100 kilometers by European convention or 80 kilometers by American convention, the two haven't settled that debate yet. More than 90% of Earth's atmospheric mass is concentrated below 16 kilometers. Altitude. Using data from the International Standardization Organization, a 1 meter by 1 meter column of atmosphere from the surface up to 20 kilometers contains approximately 10,132 kilograms of air. Now, assuming our antimatter meteor is composed of the antimatter equivalent of ordinary chondritic rock, the most common meteor composition we can assign it, a density of roughly 3,400 kilograms per cubic meter. After working through the geometry of surface area versus volume, a meteor approximately 3 times 3 times 3 meters, 27 cubic meters, with a mass of around 91,800 kilograms, would encounter just about 91,191 kilograms of atmosphere on a direct vertical descent. That means roughly 608 kilograms of antimatter, approximately the weight of a large grand piano, would survive to strike the surface. So what does 600 kilograms of antimatter actually do? Plugging the numbers into E equals mc squared, 600 kilograms of antimatter releases approximately 5.4 times 10 to the power of 19 joules of energy. Double that to account for the ground being annihilated simultaneously, and you're looking at 108 quintillion joules. For perspective, a 1 megaton nuclear detonation releases around 4.18 times 10 to the power of 15 joules. Even the most powerful nuclear weapon ever, detonated the Soviet Tsar Bomba, at 50 megatons produced approximately 2.09 times 10 to the power of 17 joules. That's still 5,000 times less energetic than our antimatter grand piano. The Tsar Bomba leveled settlements within 55 kilometers of its detonation point. Buildings of wood were reported damaged at 160 kilometers. Its light was visible from 1,000 kilometers away. Windows shattered across Norway and Finland. Now scale that up by a factor of 5,000. A 600 kilograms antimatter impact centered over a state the size of Texas would vaporize the core and devastate everything outward. But that's only the energy from what survives to ground level. The remaining 91,200 kilograms annihilated in the atmosphere would also release colossal amounts of energy, some directed upward into space, yes, but enough directed downward to extend the destruction well beyond any single state. You'd be looking at destruction across an area comparable to the entire continental United States. And remember, this is from an antimatter object the size of a car. So how genuinely worried should we be? Suppose an antimatter meteor was captured by the sun's gravity millions or billions of years ago. Could it be sitting quietly among the 40,155 near-Earth asteroids that NASA currently tracks? The reassuring answer is almost certainly not, and here's why. Space is not perfectly empty. Even in the interstellar medium, trace amounts of gas and dust drift through the void. For an antimatter object traveling through this environment, each dust grain encountered would trigger a tiny annihilation. Calculations suggest that an antimatter asteroid moving through typical interstellar space would have a survival window of only around 300 years before being reduced entirely to gamma radiation. Our solar system last had a close stellar encounter approximately 70,000 years ago with a red dwarf called Schultz's star. Any antimatter meteor swept in at that point would have had to miraculously avoid every dust grain and particle in the intervening millennia. The odds are vanishingly small. The same logic applies to antimatter comets arriving from interstellar space. Small ones would disintegrate well before reaching us. Larger ones would leave a clear trail of gamma radiation as they traveled, making them detectable by existing telescope arrays. No such gamma-emitting inbound object has ever been observed. All things considered, while an antimatter meteor impact would be catastrophic beyond almost anything else imaginable, the chances of one surviving long enough to reach Earth are extraordinarily remote, assuming antimatter stellar systems exist at all. Still, it's worth asking, if antimatter meteors did exist, might we have already seen evidence of one? An impact event of staggering destructive power that left behind almost no physical remnant of the impactor itself? On the morning of June 30th, 1908, a fireball blazed across the sky above a remote stretch of Siberia. Whatever caused it detonated in the atmosphere, rather than striking the ground, igniting enormous forest fires and flattening trees across an area kilometers wide, toppling them outward like matchsticks. Witnesses positioned more than 30 kilometers away described a flash that outshone the sun, followed by a thunderous shockwave. When scientific investigators finally reached the site in 1927, nearly 2 decades later, the scale of destruction was still immediately apparent. But strangely, for all the devastation it caused, almost no physical trace of the object itself was ever recovered. Just a scattering of microparticles. This became known as the Tunguska event, and yes, the lack of recovered material did, at one point, lead some researchers to seriously entertain the antimatter meteor hypothesis. We now know it almost certainly wasn't an antimatter meteor. The most widely accepted explanation involves a rocky or icy body that disintegrated explosively in the upper atmosphere, a phenomenon called an airburst. But the fact that the hypothesis was ever seriously proposed gives you a sense of just how strange and trace-free such an impact would theoretically be. The universe, it turns out, is full of things that could devastate our world, most of which we'll never actually encounter. Antimatter meteors sit comfortably in that category, theoretically terrifying, practically improbable. For now, at least, we appear to be safe.